Today we move on to the next lecture that is about p-values and statistical significance. And the first topic in this lecture is about what is the p-value and how to interpret it. So let's see what the p-value is through some examples. So let's say that we have a fair coin, and in this fair coin, or we assume that it is a fair coin, and we have flipped it for 20 times and we observe 16 heads and 4 tails. So can we really assume that that is a fair coin? So on average, for a fair coin, we should see 10 heads and 10 tails. So 16 heads is too far from 10. So can we conclude that the coin is not fair? So what we can do is to calculate, if we have a fair coin, what is the probability that we observe exactly 10 heads, and it is 17. What is the probability that we observe 9 or 11 heads? Actually, since the coin is fair under the null hypothesis, observing 9 or observing 11 should have the same probability, and in this case it is 16. For 10 it was 17.6%. And then we can go on and compute what is the probability of observing 8 or 12 heads and so on, down to 0 or 20 heads. So we see that observing 16 heads is relatively unlikely. So in only 0.46% of the cases, we would observe exactly 16 heads. So now we have flipped our coin 20 times, we have observed 16 heads, and we can compute the probability of observing, if the null hypothesis is true, that is, the coin is fair, what is the probability of observing a result that is at least as extreme as the one we have observed. So we have observed 16, so at least 16 or 17, 18, 19, 20. So we have all these probabilities that we have calculated here. So it would be 0.46 plus 0.1 plus 0.01 plus 0.002%, and it is as extreme to observe 16 heads or more, or observing 4 heads or less. They are equally extreme. So we have to add also the probabilities of observing 0, 1, 2, 3, 4 heads. So when you add up all these probabilities, the addition is 1.18%. So that is, if the coin is fair, you would observe a result that is as extreme as this one or more, only in 1.18% of the experiments. So if you repeat this experiment many times, flipping the coin 20 times, only in 1.18% of them you will observe 16 or more heads or 4 or less heads. So now you have to decide whether you think that this coin is fair or not. And for that, typically we compare this value to a threshold. This threshold typically is 5%. And if it is below the threshold, then we reject the null hypothesis. We think that it is so unlikely that if the null hypothesis is true, we observe such an extreme result that the null hypothesis cannot be true. So let's see a less common example. So this is really simple and we all understand it. But this is the actual use and the why all these contrast of hypothesis contrasts are useful. So let's say that we have number almost 1,000 surgical patients, And after the surgery, we apply an antibiotic ointment or an ointment without the active medication. So we split them in two halves, and in one of the groups we apply the antibiotic ointment on the wound, and on the other one we don't apply this ointment. We apply an ointment that is almost the same except for the antibiotic. And then we observe that there are 6.6% of infections in the first group, the one with antibiotic, and 11% of infections in the second group, the one without antibiotic. So the risk of infection is 67% higher, and this 67 comes from the ratio between 11 divided by 6.6. And when we compare the two groups, we don't show how to do this calculation, but you can imagine follows more or less the same philosophy as the one with the coins. So what is the probability of observing if the null hypothesis is true, that is, if there is no difference between the two ointments? What is the probability that we observe a value, a ratio between these two probabilities that are at least as extreme as 1.66? And this p-value is 1%. And then again, it is our turn to decide whether we reject the null hypothesis or not. And typically with this 5% of confidence level, we would reject it. So the p-value is the probability that under the null hypothesis, so the null hypothesis in every problem is different, but the most typical ones are the probability of observing something is fixed, as in the case of the coin, or there is no difference between the probabilities of something occurring in any one of the two groups, like in the ointments, or there is no difference in the mean between group 1 and group 2. So if the null hypothesis is true, what is the probability of observing a value, and a value for a statistic that is at least as extreme as the one we have observed? And this statistic is a small calculation. So we do a small calculation with these two ratios, with these two probabilities. We compute the ratio, and this is our statistic. Or in the case of the flipped coins, our statistic is simply the number of observed heads. So you have a statistic under the null hypothesis is distributed following a noun distribution, and then what is the probability of observing a value that is at least as extreme as the one we have observed. And it can be as extreme because it is particularly high, or because it is particularly low. And this is the difference between two tails or one tail hypothesis tests. Okay, so all these tests, they start with an alternative, with a null hypothesis. If the coin is fair, that is our null hypothesis. If the risk of infection is the same in both groups, that is our null hypothesis. So the null hypothesis is the state of affairs we want to disprove. And the alternative hypothesis is just the opposite. And you can never prove that the null hypothesis is true. What you can prove, what you can is reject the hypothesis that is true. And if you reject it, then the alternative is that the coin is not fair, or the risk of infection is not the same in both groups. Something we normally don't realize is that the p-value in itself is a random variable, and we can compute its distribution. So let's say that we have a number of observations of this. In this time, it is the partial thromboplastin time, and for two groups of patients, one in which there were blood clots that were dissolved, and another group of patients where there were blood clots that were not dissolved. These are the the partial times that we have, however they are defined in that domain. So these are the numbers that we observe in one of the groups, these are the numbers that we observe in the other group, and you may compute the p-value, but actually the p-value has so you can observe here that the two groups are relatively different. So here you see a lot of 90s, 100 something, but also some small values like 40 something. Here you have these 40 somethings, but you rarely go above 100. And here in this group you rarely go below 40. That is 126, but otherwise there are not so many values that are so low. So the p-value here, we don't have it, but let's say it is in the order of 10 to the minus 3. So that is an observation of the p-value. The p-value in itself is a random variable. So let's try to calculate its distribution, and for that we can use bootstrap. So bootstrap is a statistical technique that, given a statistic, it tries to estimate what is its distribution. So for that, let's say that we have 15 observations up here, that we have 10 observations down here. So we will compute random samples from these numbers that have 15 and 10 observations. And these 15 and 10 observations, they are obtained by resampling with replacement. So you take 15 numbers randomly from here, and every time you take a number, you put it back into the bag so that you can take it again. And the same for the non-resolved group. And then for every that is a kind of simulation of an experiment similar to this one, having kind of same distributions for the R and non-resolved groups. So you compute this the p-value for that simulated experiment, and you simulate thousands of these kind of experiments, and then you annotate what is the distribution that you observe for all the p-values that you have calculated in the simulated experiments. And here is what we would have observed, and we can put it in a logarithmic scale so that it is easier to see the distribution, because otherwise it becomes too collapsed here. So we see that the p-value is something that goes from 10 to the minus 1 to 10 to the minus 6, and with this simple data set. So we have observed in our original data set something like 10 to the minus 3. So 10 to the minus 3, we see that is somewhere close to the maximum of the distribution. And what we were not aware is that it can go really from 10 to the minus 1 to 10 to the minus 7. So 10 to the minus 7 means extremely significant. 10 to the minus 1 we wouldn't reject the null hypothesis. And actually the p-value here in the logarithmic scale looks more or less like a normal. So you can assume it is a kind of log normal. So the p-value is really a random variable, and what you observe in a particular experiment is just one of the observations. And what we can see here is that it is really unstable. So it has 5 orders of magnitude in change for a particular experiment. And actually the p-value, how far it is from the threshold that you decide, tells you how likely it is that if you repeat the experiment you will have the same rejection or non-rejection of the null hypothesis. So let's say that you have a p-value, you make an experiment and you have a p-value that is 0.04999999. So you reject the null hypothesis because it is below the 5% threshold. But how often or how likely do you think, if you repeat the experiment, how likely it is that instead of having 0.049999, now you have 0.05000001? So in that case, you wouldn't reject the null hypothesis. And it is very likely because we have seen that the p-value is rather unstable, and sometimes you will fall below the threshold level, and sometimes you will fall above the threshold level. And falling below or above means rejecting or non-rejecting the null hypothesis. So actually, if you are just in the middle, so just at the threshold, there's a 50% chance that you fall in either side of the rejection condition. So here all this reasoning is formalized, and there is this paper where they reason how likely it is that you can replicate the same result, so rejection or non-rejection, depending on the p-value. So if the p-value is very low, then with a given sample size, it is very likely that you will always have the same replication. So if you reject, you always reject, because the p-value is so low, here it is 10 to the minus 5, that no matter how many times you repeat the experiment, you will always reject. But if you are just at the threshold for rejection, then there is a 50% probability, and this is what this 0.5 means, that you fall in either side of the rejection side. And this is worrying. So if you have a p-value that is close to the threshold, it is rather recommended that you repeat the experiment, probably with a larger sample size, so that you can better see what is the effect of your treatment. Here is another example. So this is again simulated data, because we need to know what is the ground truth. So let's say that we have two groups in which we are measuring whatever value, and here is a verbal ability, but we are simulating the value, so it doesn't matter what it means. And we have a mean difference between the two groups of 10, but the standard deviation in each one of the groups is 20. So the effect size, that is the ratio between the mean difference and divided by the standard deviation, it is 0.5, which is a relatively small effect size. So we simulate data, and with this simulated data, we simulate data for the one of the groups, for the other group, and then we compare whether this difference is significant or not. And we compute the p-value for that comparison. So we have some p-values like 0.05 and 0.04. So that means there is a significant difference. Actually, we know that there is a significant difference between the two because we have simulated the data, and that was the case. Some of them, they are extremely small, smaller than 0.01, but some of them, they are extremely large, and we have here 0.75 or 76, 0.24, 0.61. So some of them, they are really large, and despite of the fact that there is a real difference between the two data sets. So but simply by chance, we have been unlucky with our samples, and then it seems that there is no difference between the two groups. And we see here that the p-value goes from 10 to the minus 3, smaller than 10 to the minus 3, to 0.76 for an experiment in which we know that there is a difference. So rather than p-values that are very unstable, it is much better to use confidence intervals, and we'll see now why. So for each one of these experiments, we compute what is the confidence interval of the difference. So the confidence interval for the difference here is this one, this segment, and the fact that this segment doesn't include 0, that 0 means 0 difference, is what makes the hypothesis contrast to reject the null hypothesis. So because the confidence interval doesn't include 0, we reject the null hypothesis. And so there is a direct relationship between this confidence interval and the p-value. Actually, the p-value somehow measures how far this confidence interval is from the limit. So here we reject the null hypothesis, here we don't reject, here we almost reject because it is very close, and you see that we almost rejected it, or we rejected it just by a very little margin. Here we don't reject, and so on. So if you look at the confidence intervals, even if you don't reject, here you don't reject, but it gives a better impression that there seems to be a small bias to the right, meaning that it seems to point out that there is a difference between the two groups, although this difference is not significant because the confidence interval includes 0. But if you look at the confidence interval that looks pretty wide, you might think that if you increase the sample size, that will make the confidence interval to be smaller, then you might be able to identify what is you might be able to identify that the difference between the two groups is really significant. Actually, if you look at the central values of these confidence intervals, you see that they are almost more or less centered around the true difference. So the p-value is a rather unstable and widely varying random variable, while the confidence interval is much smoother and conveys better the idea that there is a difference between the two, although that difference might not be significant. Here, for instance, in this extreme, we were particularly unlucky with the data, and then the two groups seem to have almost no difference. It is very, very close to 0. That is why we have such a high p-value. So there is a direct relationship between the p-value and the how far the confidence interval is from the 0 difference. So how to interpret the p-value? So we have computed the p-value for the comparison of the mean in two groups, and the p-value is 0.03. So what does it mean? It means that if the two population means were identical, that is the null hypothesis, there is a 3% chance of observing a difference that is as large as the one you have observed or larger. This is as extreme as the one we have observed. Or another way to read that would be random sampling from identical populations would lead to a difference smaller than what you have observed in 97% of the experiments and larger than that in only 3% of the experiments. And now we have incorrect ways of reading that p-value. So an incorrect interpretation is that there is a 97% chance that there is a real difference between the two populations and a 3% chance that the difference is just a random coincidence. Or the p-value is the probability that the result is due to sampling error. The p-value is the probability that the null hypothesis is true. The probability that the alternative hypothesis is true is not 1 minus the p-value. The probability that the experiment will hold up when repeated is not 1 minus the p-value. and a high p-value does not prove that the null hypothesis is true. So if you cannot reject the null hypothesis, that doesn't make it true. And here is an interesting psychologic, if you want, interpret how do we react to p-values. So if the p-value is very small, we say, oh, this is highly significant, and we are happy. If we are just close to the threshold, we call it significant. We are not so happy. And if we are just at the limit, we redo the calculations just to make sure that we didn't do any mistake, and just to see if we can push it a bit to the rejection side. If it is just very, very close, but on the other side of the rejection, so we cannot reject, we say that our results are on the edge of significance. If they are somewhere below 0.1, so we say that they're highly suggestive, significant at the 0.1 level, that so we relax our threshold so that we can reject it still. So we normally have an interest in our alternative hypothesis. We want to show that our treatment is useful, that that there are differences between these two groups. So we try to do our best to make the data speaking on our behalf. And if it is larger than 0.1, then we start looking at subgroups, trying to see if for any one of these subgroups we can find significant differences. And we have already talked about this problem. This is the multiple testing, and it is also this problem of data snooping, taking decisions and trying to interpret the data once you have collected the data. And looking at this example where there is a difference, but the data, sometimes you are unlucky with it. So if you start looking at subgroups, even if there is no difference between the subgroups, maybe you are lucky in that case. So in that case, you find a relationship between two of the subgroups that is really doesn't hold if you try to repeat the experiment. So taking decisions and looking for features that are different in two subgroups once you have collected the data is not really a good practice. So that is all for today, and see you tomorrow.